All right, so let's just recap where we left off. When we wrapped up the nervous system, we were talking about the efferent nervous system. And we discussed in pretty good detail how the efferent nervous system can autonomically control involuntarily different organs inside our body. And we said that most of our involuntarily controlled organs, are dually innervated by both subdivisions of the autonomic nervous system. So we compared and contrasted the sympathetic from the parasympathetic nervous system and their effects on various target tissues. We then left off without going into any detail about the somatic efferent nervous system. But we at least know that the somatic efferent nervous system is a way to voluntarily control various skeletal muscle organs. And so that's why we're going to come back and look at this voluntary control of our somatic nervous system. In the somatic nervous system, our somatic nerves, if we look at the anatomy, the somatic nerves are just a single nerve which extends to the target organ. If you recall, the autonomic nervous system was actually two nerves in a chain. There's a pre- and a post-ganglion cell. In the somatic nervous system, there's just one nerve that extends from the central nervous system out to the effector organ. So it's just one nerve. Because they are still motor controlled, they would still be located on the ventral side of, say, for example, the spinal cord or even the brainstem where they're located. Additionally, you can add about the anatomy of your somatic nerves is that they are myelinated, actually very heavily myelinated. Your somatic nerves are heavily myelinated. Somatic nerves are very heavily myelinated. That means what? Fast, right? Conduction velocity. So they can conduct action potentials very quickly. Furthermore, the somatic nerves always release acetylcholine. There's no variation here. The somatic nerves always release acetylcholine. Additionally, any skeletal muscles innervated by the somatic nerve are going to have nicotinic cholinergic receptors. And just to refresh your memory, it's those nicotinic receptors, which are just basically chemically gated or ligand-gated sodium channels. So when acetylcholine is present, sodium channels open up at the skeletal muscle. And what's the effect? Eventually it will. We're going to learn that it's not so fast or simple. But if I open up a gated sodium channel, what's going to happen at the muscle? It's going to depolarize. So acetylcholine at a skeletal muscle is going to cause the skeletal muscle cell to depolarize. And then we'll pick up here in lab this week, and then continue our discussion when we get to chapter 12, probably next week. We'll look at skeletal muscle physiology. But just to kind of give you a heads up, the skeletal muscles are going to work a lot like nerve cells. You know, they're going to grade up to what? Grade up the threshold and generate an action potential. So regarding the anatomy, our somatic nerves are very heavily myelinated. It's one nerve which extends to the target tissue, and it always releases which neurotransmitter? Which neurotransmitter does the somatic nerve release? Acetylcholine. And so therefore the muscle has to have which type of receptors? The nicotinic receptors. Nicotinic receptors function as what? They are a class of cholinergic receptors. What do they function as? What do they do? They open for sodium. And so yes, they are excitatory. And the muscle doesn't just immediately contract. This could take us a good day to talk about what happens within a portion of a millisecond before the muscle contracts. What questions do you have about this basic anatomy of a somatic nerve? If we look at it a little bit closer, multiple nerves may innervate a particular skeletal muscle. And in that case, these things are called motor units. And so this should sound familiar from your lab, pre-lab this week. A motor unit is going to be a single somatic nerve, and then however many muscle cells or muscle fibers it innervates. Again, a motor unit is a single somatic nerve, and the number of skeletal muscle cells which it innervates. Motor unit is one somatic nerve and an X number of skeletal muscle cells. That number of muscle cells is variable. We'll come back to this when we get into the chapter 12, the skeletal muscle physiology, about why we might need different sized motor units in our body. But figure 11.14 tries to help you visualize what's going on here. So we've got 3 motor units shown here. What's labeled as motor unit number 3 is colored in purple. 2 must be red and 1 must be blue. They're just kind of arbitrary values there. But if you look at them closely, motor unit 1 or 2 or 3, if you look at the termination, if you look at motor unit 1, it's going to control 1, 2, 3, 4 skeletal muscle cells. What's labeled as motor unit 2 controls just 3 skeletal muscles. And then the other one controls how many? Motor unit 3 controls 3 muscle cells. Is it muscle cell or muscle fiber? Muscle fiber is the more accepted term, but it is a cell. You can interchange it. I just keep repeating cells so you don't think of something non-cellular. Okay, so I want you to realize it still has a membrane, it still has a nucleus, it still metabolizes, it still has receptors, and etc. But if you go out and become an anatomist, fiber is the most accepted term to describe a cell. That's a good question. So a muscle fiber is another term for a muscle what? Cell. And so the most accepted term is shown here in the textbook, fiber. So when a single motor nerve gets excited, not just one muscle cell gets excited, how many? X number, however many it's controlling in that motor unit. So you're going to have one nerve cell controlling lots of muscle cells simultaneous. You start getting a big, strong response if there's a lot of muscle cells controlled by that motor unit. Okay. What additional questions do you have about using the term motor unit, or how it's kind of defined, I guess? We became introduced to this term called reciprocal innervation when we described our spinal reflexes. What is reciprocal innervation? So without this reading, what does it mean? We are going to... Very good. The opposite, right? What that means is when you're doing some type of voluntary movement, you need reciprocal innervation. That's talking about muscle organs are reciprocally innervated, oppositely innervated, meaning to do a motion, some muscle organs would be excited. At the same time, other muscle organs would be inhibited so that we can get some type of motion. We did the little reflex, didn't we? Saw how our muscles, some contracted, some excited. That's because of the motor units are going to be all simultaneously. Some will be excited and others will be inhibited. And so the reciprocal innervation is a term which we can associate with the somatic nervous system. Thinking back, what term did we talk about that we associate with the autonomic nervous system? Dual innervation, meaning both fibers, sympathetic and parasympathetic fibers, are activating in the same organ, right? In this case, we're looking at different organs acting at the same time, not in set manners. And we saw this little simple reflex, right? If you burn yourself somewhere, you need to get your limb out of the way, basically. So we need reciprocal innervation to help pull that limb out of the harmful situation. And if we get an introduction to what we're going to study in chapter 12 and become introduced in lab this week, what does the muscle cell do? What happens in the skeletal muscle cell is that it first depolarizes because the nicotinic receptors are gated sodium channels. When acetylcholine is present, sodium is going to flood into the cell to cause a graded depolarization. The skeletal muscle will then, that depolarization opens up voltage-gated channels, which initiates what? If I open up voltage-gated channels, that cell is going to hit what? Threshold to generate an action potential. So your muscle cells are going to work a whole heck of a lot like your nerve cells, maintaining rest, depolarizing the threshold, and generating an action potential. And then I've got a bunch of ellipses here. Eventually, take us a couple of days, eventually we'll get to muscle contraction. So it's not so simple. It's not very direct, if you will. All right, so this is all given for you. If you don't have your guided notes, it'll be printed for you. So I want to go ahead and transition to figure 11.15 so we can get a visual of what's going on. In order for a somatic nerve to tell a skeletal muscle to contract, the only way it's going to do it is by releasing acetylcholine. Our somatic nerve is shown in the yellow. Acetylcholine will be released. And we're going to modify our terminology. Instead of calling it a synapse, we're going to call it a neuromuscular junction. Because it's a junction between a nerve and a muscle. So acetylcholine diffuses across the neuromuscular junction and binds with, which is called, what's our receptor? The nicotinic. So go ahead and label this if it's not already on your guided notes. Label that as a nicotinic receptor. It's more permeable to sodium, and the effect is what? Sodium floods in, the effect is depolarization. Maybe you want to draw next to it over here a voltage-gated channel. Voltage-gated sodium channels. This is figure 11.15 in your textbook. So anatomically speaking, our somatic nerves are myelinated. There's just one which extends to the effector organ. They always release acetylcholine, and the skeletal muscles always express sodium or nicotinic receptors to become permeable to sodium, which causes excitation. And with that, I'm going to leave you hanging until we finish up the endocrine system. So before we get into the endocrine system, what questions do you have over the somatic nervous system? All right, so let's transition now into good old endocrine system. All right, so we're now transitioning to the endocrine system. I know numerically it's out of sequence. And again, to remind you, the reason we pulled it out of sequence is so we get all the nervous system compartmentalized into a single unit test instead of dragging all that into this unit, which I'm going to guess you're probably okay with that. But the correlation is in Chapter 6 material, we actually became familiar with when we studied Chapter 5, extracellular messengers. We're still going to see some common themes. And now we're still going to look at an extracellular messenger. We're still going to have a source, we're still going to have a target, and we're still going to have a response. So all that is going to be similar. What is different is that our endocrine system specifically releases things called what? Hormones. And they go into the blood to act on various receptors on target tissues to bring about various responses. What we're going to do is introduce just generically some terms that we'll need to understand the endocrine system. And in the balance of it, probably 2 days, we're going to look at specific hormones and specific responses. Okay? So therefore, it's going to be real important for you to read and reread chapter 6 to kind of make it sink in. So without it, it's just going to be really terribly confusing. I don't want you to be confused, I want you to understand how the endocrine system works. If we look at some objectives of the endocrine system, the first thing we're going to do is differentiate a primary and secondary endocrine gland. We're also going to go through some different specific glands, their major targets, and the primary effects of different hormones at the targets. So what does a particular hormone predominantly do? Then we're going to go back and reintroduce the hypothalamus and how it's anatomically related to each the posterior and the anterior pituitary. We're going to reintroduce this term tropic. What does tropic mean? Tropic hormone. A hormone which stimulates another endocrine gland. It stimulates or even inhibits the release of another hormone. So it targets an endocrine gland. Looks like I had some numbering. This should be item 5. Okay. But we're also going to look at how hormones interact with one another if they're acting at the same time. And we're going to define synergistic permissiveness and antagonistic types of responses. So before we get into the details, I want to give you a few reminders. Just like we've seen before, we need to talk about the relationship of a receptor, the control center, and the effector. And so the target tissue is probably going to have all of these things. The target tissue is going to express the receptor for a particular hormone. It's going to integrate with how it should respond and bring about the effect. So for example, if I have insulin in my blood and I target, say, a fat cell, the fat cell is going to have an insulin receptor. And it's going to have a cascade of events that'll say, well, we need to do this. And then what would the cell do? What would be the effect, or the effector in this case? What does insulin tell your cells to do? Not release it. Stop it. Not only inhibit, but what? Store. So the effect is, say, my fat cell would say, well, take in glucose and other lipids that are in the blood and then store them. Right? So it promotes anabolic-like reactions. And so all of that within the target is happening here. So that same relationship that we introduced way back in August still holds true here in the endocrine system. Okay. Additionally, chapter 5, we need to recall our extracellular messenger, right, terminology. Here we're looking at hormones and some neurohormones. We've got to take into consideration the solubility. If it's more lipophilic or hydrophilic, that's still critical to the endocrine system. And as well the location and the structure of the receptors. All still very important to understand how the endocrine system functions. And so just a reminder, we're still going to differentiate a source cell. That'll be the secreting cell or the endocrine gland cells. The target cell is going to have specific receptors. So all these components are very much related to the endocrine system. Visually, just to remind, we also talked about neurohormones. Okay, same thing. We still have a source. The messenger would be the hormone, and the target would still have a receptor. So all of chapter 5 is still applicable here, including as well the solubility of particular hormones. If you recall, what kind of hormone is this? What type of solubility would this hormone have? There's just no way to do that, is there? It'd be like a lipid, okay? So we didn't use hydrophobic, we would have said it is lipophilic. How'd you know it was lipophilic?
Down to a protein.
A couple of things that diffuse out, and it's also we see it down to carrier. So this messenger at some target cell, the receptor would be located where? inside of that target cell to activate what? Lipophilic messengers tell target cells to do what? Initiate protein synthesis, so transcription, and protein translation. What do hydrophilic messengers tell your receptor to do? Or your cell, excuse me. Hydrophilic messengers bind to receptors located where? On the cell membrane. May eventually tell it to make a protein, or may just do what? Open an ion channel, proposal, or activate a second messenger system, which who knows? Could activate transcription, cell division, just you name it, can activate. Alright, so we did good with that. We also just reiterated that our receptors are also built differently, so the responses are variable. What we're trying to illustrate with this image from chapter 5 as well. Okay, so all of our receptors are built differently because they function differently. Okay. So a lot of reminders here, right? Just to reiterate, this class builds all semester, right? We can't just brain dump from unit to unit. We're accumulating all semester long. If we look into the endocrine system more specifically about what's happening, we'll be able to differentiate a primary from a secondary endocrine gland. But before I do so, it looks like I want to show you a video. So let me. All right, so what we want to do is now differentiate the different types of endocrine glands that we have in our body. Some are categorized as being primary endocrine glands, and others are categorized as being secondary endocrine glands. The difference between a primary and a secondary endocrine gland is that a primary endocrine gland's primary job is to do what?
Secrete hormones.
Secrete hormones. So the primary endocrine glands, their primary job is to produce hormones. So when you think about a primary endocrine gland, you try thinking of like the pituitary gland, for example, or cells in the pancreas, which make insulin, or glucagon, for example. However, there are other glands which are categorized as being secondary endocrine glands. How do you think about secondary endocrine glands? How could we define those?
Secretion is secondary to other functions.
Okay, so their secretion of hormones is secondary to other functions. Very good. A great example is the heart. When you hear the word heart, you probably think of what? Function-wise. What?
I did the heart there.
Pumping.
Function-wise.
So function-wise, what do you think? What's the job of the humping?
Pumping blood.
But the heart is actually an endocrine gland as well. It secretes a hormone called atrial natriuretic peptide. You don't have to write that down unless you want to. You can abbreviate it ANP. But it does produce a hormone. However, that's not its primary job. We need it first to pump and distribute blood. Secondarily, we need it to produce this hormone called atrial natriuretic peptide, or ANP. Atrial natriuretic. What do you think it has to do with? Sodium and
Your blood pressure.
sodium, blood pressure, blood volume. And so it probably targets your what'd you say? It doesn't target the cardiovascular system. What'd you say? I don't know that it does. It may also target the thalamus, but what it primarily targets is your kidneys or sodium elimination. So that when you eliminate sodium, water follows it osmotically. So your blood volume goes down and your blood pressure goes down to set point. All right, so we'll get into into other pathways as well. But the point of that is that the heart is a secondary endocrine gland. It produces a hormone called AMP, for example. All right, so the glands that we're going to study, we're going to talk about the hypothalamus, the pituitary, the thyroid gland, the parathyroids. We're not going to talk about the thymus. We probably won't, I don't think we're going to talk about the pineal gland either. We'll talk about the adrenal gland in good detail, pancreas, ovaries, testes. We won't talk about the placenta, but let's see, the kidney. So we'll talk about most of the primary endocrine glands. Furthermore, if we want to release hormones, we have to have some type of stimulus, right, to activate the receptors at the secreting cells. And there are three major categories in which hormones can be released. The two should sound familiar to us. What are our major controllers for our body? The brain, which is which type of system? Nervous system. So our nerves, right? What else? What's our other major controller? The endocrine system, so hormones. Yeah, so those two will be familiar. So let's introduce these. If we're looking at the control of the release of a particular hormone, our hormones may be regulated neurally. So that means a nerve can activate a gland to release its hormones or neurohormones into the blood. Great example is the adrenal medulla, which we introduced in chapter 11. We actually called it a modified postganglion nerve. It releases, do you remember what it releases? Adrenaline into our blood. So we talked about it being a neurotransmitter in chapter 11, but honestly we said it could be a neurohormone. And so we're looking at it as far as just being a hormone in this category. So the nervous system can activate the release of hormones. So in addition to adrenaline from the adrenal medulla, some other examples include the release of oxytocin, you can abbreviate OT, from the posterior pituitary. And another one is called ADH, antidiuretic hormone, also from the posterior pituitary. The release of these hormones are neurally regulated. Hormones can activate the release of other hormones. What word do we use for that though? Tropic. So the third panel over here, tropic stimuli or hormonal stimuli can activate the release of some hormones. So for example, like we said in our lab last time we met, hypothalamus tropically regulates the anterior pituitary. So we're using these releasing and inhibitory hormones. What was the tropic hypothalamic hormone we studied in lab 2 weeks ago? TSH, does it come from the hypothalamus? TRH, thyrotropin releasing hormone, tropin, tells you, thyrotropin releasing hormone, is tropin, to which hormone? Anterior pituitary, to release which hormone? TSH. TSH from the anterior pituitary is tropic to the thyroid gland, to release thyroxine. Okay. So tropic means a hormone can stimulate or inhibit the release of another hormone. So hormones can activate the release of some hormone. We'll call it tropic. You'll see the tropic with or without the H. I like to throw it in. What may be new to you is humoral stimuli. Anybody know what humoral stimuli are? Humoral. What? Something in the blood. Factors in the blood that aren't neurotransmitters and that aren't what? Hormones. Can also activate the release of some hormones. A great example is what we just showed a moment ago. The release of insulin is humorally regulated by which blood factor? Which blood factor could humorally regulate the release of insulin? I don't think calcium would actually affect insulin release, not directly anyway. Glucose, so blood glucose, humorally regulates the release of insulin. Blood glucose humorally regulates the release of glucagon, depending on if the levels are too high or too low or whatever the case may be. Calcium can humorally regulate two hormones. One is shown in this image. Blood calcium levels humorally regulate the release of which hormone shown here? What's it abbreviated as? Sorry, Stephen, get it. What's it called? PTH, parathyroid hormone, is humorally regulated by calcium. There's another hormone called calcitonin, which is humorally regulated by, what do you think? Calcitonin, humorally regulated also by calcium. So if a nerve stimulates the release of hormone, we would say it is neural. If a hormone stimulates the release of another hormone, we call it tropic. And if something in the blood that's not a hormone or neurotransmitter, we would say humoral. Furthermore, we've got to take into effect that not just one hormone is expressed in your body at one moment in time. You're going to have dozens of different hormones circulating through your body at the same time. And therefore, we need to look at how they would interact with one another. If we look at hormones, we can kind of group their relationship into either being permissive, synergistic, or antagonistic to one another. I'm going to start on the far right of this image because I think you've probably used this word before, antagonism. If two hormones are antagonistic to one another and they're expressed, what does that mean? They're opposite. Their actions are opposite. Hormones can't like or dislike each other. So their actions are opposite. I've actually listed a couple of scenarios of hormones which are antagonistic. Which two hormones have we named so far which are antagonistic to one another for regulating blood glucose levels? Insulin and glucagon. Glucagon are antagonistic. So insulin would do what to our blood sugar? Lower it back to set point. So glucagon must raise it back up to set point. A second example of an antagonistic relationship between hormones is shown in the panel, the second panel in the previous image. Parathyroid hormone is humorally regulated by calcium levels. What does parathyroid hormone do? Can you read it in that image by chance? What does parathyroid hormone do? Two tiny. Parathyroid hormone is humorally regulated by low blood calcium. And so what do you think its effects are? Raising blood calcium back up to that point. It is antagonistic to a hormone called calcitonin. So what does calcitonin do? Lowers blood calcium levels back to that point. So calcitonin and parathyroid hormone are an example of two hormones which are what? Antagonistic to one another. Some hormones express a synergistic relationship. What do you think about synergy? They help. They enhance. Not only do they help, they actually enhance the response by the target cell. So both are present. So for example, like thyroxine, what does it regulate? metabolism. So I could say, right, so it brings our metabolism up to set point, right? I could say thyroxine is synergistic with adrenaline. So my metabolism is not only elevated, but it's not only brought up to set point, it's what? Maybe over set point. Okay, so it's exceedingly high through that moment of time. So the effects are synergistic with one another. Additionally, some hormones may be categorized as being permissive one another. And one way to define it is that they both need to be present to bring out effect in the target tissue. Some hormones are permissive to one another. They should both be present to bring about a response. All right, so those are some terms we could talk about the relationship between different hormones. But we also can address, well, what if the endocrine system goes awry? And what we can do is look at different types of diseases or disorders. The reason a person might have an endocrine disorder is just simply due to abnormal concentrations of a hormone. So if hormone levels aren't at set point level, they're either above or below set point. And we're not in homeostasis for whatever hormone that is. If the hormone levels are below set point, we would refer to that hormone as being hyposecreted. Conversely, if the levels are exceeding, we would say that hormone has been hypersecreted. And that's kind of the easy way to look at, like, there's something, if you're like, oh, the hormone must be too low or high or whatever. However, if someone has a disorder, you need to broaden your scope and say, well, maybe it's not the endocrine gland over or under secreting the hormone. What could the problem, where else could the problem lie? Where else could the problem lie? If it's not the actual hormone itself, at the target cell. Yeah, so maybe the target cell isn't responding fast enough or at all. Or its receptors are there, but they're built wrong for whatever reason, and the cell's not able to respond. So it could be a target tissue problem why someone may have an endocrine disorder. So the endocrine system is really cool when we look at when it's wrong, right? When it's not working. However, before we figure out what's wrong, we need to understand how the endocrine system operates normally under homeostatic conditions, and that's what we're going to do. Is look at what are these hormones, what do they normally do? And then we can go on and introduce factors. And try to figure out, well, it may be this, it may be that. And so the question is, what are we going to focus on? And you'll see a pattern here. We're going to go through each of the glands. And of each of the glands that we choose to study, we're going to identify the hormonal hormones which are released. Notice it may be plural. Some endocrine glands may release multiple hormones, like the hypothalamus, where this is not just TRH, it releases another 7 more tropic hormones to target the anterior pituitary. Anterior pituitary releases 6 hormones. Okay, so we're going to go through and address each of those. We're also going to look at the most prominent regulator or regulators. There may be multiple regulators for the control or of the release of particular hormones. And then we're going to look at the major targets and the major functions. Why don't you go ahead and clarify that? We're going to look at write the word major functions. We're not going to be able to be all-inclusive. It's not an endocrinology class. It may feel like it for the next week, but it's not an endocrinology class. And so we're going to say, well, usually it does this. And so when I talk about the major functions, we'll highlight, there may be sometimes just gender association. But if you're going to say, well, in the female, hormone X does this, it would also have a function in the male. It might be slightly different, but males and females have the same hormones under normal operations. And so females have estrogen, so do males. Males have testosterone, so do females. the balance between the two, right, the concentration might vary between the genders, but they're still present. All right, and so what that does is this transitions us now to getting into specific pathways. So before we get into specific pathways, I want to take a moment to field any questions that you may have about just the general operation of the endocrine system, about using some terms, relationships, and etc. So this is where you just like buckle in endocrine system pathways. And it's going to take a lot of repetition to kind of make the connections. We're going back to the good old brain. I know we're in the endocrine system that several endocrine glands are present in the brain. One of the glands we saw in our dissection is the pineal gland. I don't think I'm presenting it to you. I don't recall. But the pineal gland, just out of trivia, which hormone does it release? Which hormone does it release? Do what?
Cortisol?
Not cortisol.
Melatonin?
Melatonin. The pineal gland produces melatonin to help you go to sleep at night. But what I want to focus here on is the relationship between the hypothalamus and the pituitary. The hypothalamus, if you recall, is very important to basic maintenance, homeostasis for almost everything, including the endocrine system and controlling how it works with the pituitary gland. So we're going to zoom in and look at anatomically what's happening, the relationship between the hypothalamus and the anterior, and then also the posterior pituitary. If you remember from our sheep brain dissection, it didn't look too exciting, did it? But these cells are so profoundly important and diverse in their function. So the hypothalamus, just zooming in, is connected by an area which is called the infundibulum. And it connects that anterior and posterior pituitary. If you recall, we could see those on the underside of the brain when we looked at the cranial nerves. All right, so the hypothalamus, what it does is it produces, I'd go ahead and call them neurohormones. You can call them hormones if you want, but we know it's coming from neural tissue, so I think more precise will serve you better. It produces two kind of types or functioning classes of hormones. A couple of its hormones may actually be secreted from the posterior pituitary. So notice this nomenclature. The hypothalamus makes hormones that are in the hypothalamus but are actually released from the posterior pituitary. So the posterior pituitary doesn't actually produce its own neurohormones. It just is a source of release or secretion. In the relationship with the anterior pituitary, it tropically regulates it. So that tells us produces hormones that go into the blood and then target the anterior pituitary. What we're going to iterate by looking at some of these images is that the hypothalamus, which is basically these nerves extend down to the posterior pituitary. However, they do not extend down into the anterior pituitary. So there's going to be a blood connection between the hypothalamus and the anterior pituitary. Okay. And so let's turn to figure 6.3 in your textbook. And you have it for you in your guided notes and enlarged. If you look at this image closely, a couple of things we can see are familiar looking, hopefully it's familiar looking, nerves. You can see the dendrites of the cell body clustered together, our nerve cell axons, and then down here, and what's called the posterior pituitary, are what part of our nerve cells? The axon terminals. So your posterior pituitary is just axon terminals of nerve cells that originate where? In the hypothalamus. So label that top area as the hypothalamus. where these nerve cells are located. Label that as the hypothalamus. And then you've got the axon terminals in the area, which is labeled as the posterior pituitary. Carries our hypothalamic neurohormones from the posterior pituitary out into the circulatory system, system-wide distribution. There are two neurohormones released by the posterior pituitary, and they include a hormone called oxytocin, which we've become introduced to. You can abbreviate OT, oxytocin. And another hormone released from the posterior pituitary called anti-diuretic hormone, or ADH, anti-diuretic hormone. They release posterior pituitary, they release oxytocin and anti-diuretic hormone out into the general circuit once the hypothalamus initiates its release. We'll come back to the hypothalamus in just a moment. I want to anatomically compare the posterior pituitary to the anterior pituitary. Okay, so looking at figure 6.4, something should look pretty darn different here. What are some differences? The blood direction actually isn't reversed. It's still coming out. What?
She was just saying it did.
Do what?
She was just repeating.
Oh. What is different? So the direction of the blood flow is still similar. So let me out away from the brain. The quantification isn't precise in this one. There are no terminals where? In the anterior pituitary. If you look at the anterior pituitary, you notice that there aren't any nerve cells extending into there. The nerve cells which control the anterior pituitary terminate where? The area is called the infundibulum. The infundibulum. You notice you would have more than two nerve cells in the hypothalamus. It's just trying to. Yes, there's actually quite a few because there's so many neurotransmitters that have to be made to control the anterior. There's 8 different neurotransmitters made that control the anterior pituitary. So the difference between the anterior pituitary is that it's not neural tissue, it's actually just glandular, or you could say endocrine tissue. I'm going to keep it simple. And it'd be best if this were shown all over, like these little gland cells shown all over the anterior pituitary. But the anterior pituitary is not intrinsically regulated. It is how? Extrinsically by the, and what, how? Using our 3 new term, tropically, by hormones from the hypothalamus. So the hypothalamus has to produce these tropic neurohormones. They go into this very special circulatory system and then drain over to the anterior pituitary. Okay? And then under the appropriate stimulus, the anterior pituitary hormones are released out into the general circuit. So the little blue dots, what are these representing? Which ones? Yes? Which one? Yes, neurohormones. Tropic neurohormones from the hypothalamus. Get released through the special portal system that shunts blood from the hypothalamus right over to the anterior pituitary. This is a very special and a very unique blood circuit system in that it gives us direct shunt from the hypothalamus over the anterior pituitary so that our neurohormones don't have to go out to the general circuit, into the heart, distributed everywhere, and then hopefully maybe get back to the pituitary. And so it's just a way to get a low concentration of hormones right to the adjacent organ and anterior pituitary. There are 6 different anterior pituitary hormones that we're going to study. We'll get introduced today, which some are trophic and some are non-trophic, targeting some endocrine tissue and others non-endocrine tissue. Before we study the posterior pituitary in better detail, what questions do you have about the anatomical differences between the posterior and the anterior pituitary and their relationship with the hypothalamus? What kind of cells are in the posterior pituitary? Nerve cells that actually originate where? In the hypothalamus. What type of tissue is in the anterior pituitary? Endocrine glands. They are nerve. There's no neural tissue in the anterior pituitary. All right, so what I want to do is introduce the posterior pituitary hormones, and then when we come back on Thursday, we'll introduce our anterior pituitaries and probably hormones and probably move on out of it as well. But I want to use, after we finish this up, I'll use the remainder of the class time to go over our exams, our Unit 2 exams. So if we look at the posterior pituitary, it's properly called, or AKA, also known as, the neurohypophysis, reiterating that this has what type of tissue in it? Neural tissue, nerve tissue in it. We also kind of mentioned that the posterior pituitary doesn't make any hormones. It just simply does what? Releases them or secretes them. Okay. The 2 neurohormones which it secretes include oxytocin and antidiuretic hormone. I may or may not have given you a little heads up in the Endocrine System lab about the abbreviations. The abbreviations are good if they're used properly, but if you get a couple of letters transposed, you may mean a completely different hormone, which is then an inaccurate pathway. So what I recommend is you not learn the abbreviations first. Study the name. Once you understand the name and its function, then you can probably be more confident in using the abbreviation. A lot of the hormones will tell you what they do, where they came from, or where they target. A lot of them give you something that you can kind of decipher. Even if you don't know the pathways, you can read the name. Like antidiuretic hormone is a hormone that, what do you think? Anti means inhibits, reduces the water what? Loss. Okay? So it inhibits the loss of water. What do you think it targets? The kidneys. Okay, so we didn't even study this pathway. You know, well, ADH, and wouldn't have told you anything, but antidiuretic hormones and lab prevents water loss, and those target our kidneys where our water is removed. That's exactly it. Oxytocin doesn't necessarily give us anything directly, but we hopefully are becoming familiar with this one because we saw it in our positive feedback pathway as an example early in the semester. So what we're going to do is introduce these 2 neurohormones and talk about the regulation, the target tissue, and the primary response or function of that hormone at a particular tissue. It may be useful for you when you're looking at the hypothalamus or the posterior pituitary to actually keep maybe the image out, figure 6.3 out next to you, so you can kind of figure out what the relationship is. So the posterior pituitary, one of its neurohormone which it releases is called oxytocin. How is it regulated? Of our 3 options, how do we regulate it? Did I hear it? Neurally, by the hypothalamus. Okay, the hypothalamus neurally regulates the release of oxytocin. What do you think it targets? What do you think it targets?
Where did we see this hormone in play in our example? It actually, I don't think it targets the pituitary. What do we see? The what? The uterus. Do you know what part of the uterus? Portion of it. Specifically the smooth muscle of the uterus. Okay. Tells the smooth muscle in the female uterus to do what? Contract. Yeah. It also targets smooth muscle in the female and the smooth muscles lining the ducts, which produce milk, and the mammary glands. Okay, so milk ejection. In the female, oxytocin is important for what we call parturition or childbirth, for the contractions during birth, and also the milk ejection or delivery. The milk, which would hopefully happen after a baby is born. So since it targets the smooth muscle in the female, it targets smooth muscle contraction. How is it, what type of feedback mechanism? Which one? Positive feedback mechanism. In response to existing levels of oxytocin. We'll keep it surging until the placenta is delivered, until the milk is delivered, and so on and so forth. So that's one neurohormone released by the posterior pituitary. A second neurohormone released by the posterior pituitary is called what? Antidiuretic hormone. Is it made in the posterior pituitary? No. Okay. It is also known as vasopressin. That's the proper name, but I like antidiuretic hormone. It tells me a lot more. I'm just kind of walking in not knowing anything. I think antidiuretic hormone gives a lot of background information. How is it regulated? Neurally by the hypothalamus. Hypothalamus is going to initiate its release. What does it target? Targets your kidneys. It also targets the smooth muscle in your blood vessels. My abbreviation BD stands for blood vessels. It targets the smooth muscle in your blood vessels. What do you think it might do at your kidneys? We said it will regulate water loss. And so what we want to do is promote water retention or absorption. At your blood vessels, what do you think your blood vessels will do with antidiuretic hormone? If I want to bring my blood pressure up, my blood vessels will probably constrict. Okay. And so some primary functions of antidiuretic hormone is promote water retention at the kidneys and vasoconstriction at your blood vessels to help bring your blood volume and your blood pressure back up to set point. So that tells us when we get in the last unit or last chapter, the kidneys, we're going to talk about antidiuretic hormone. The chapters preceding it, when we talk about blood vessel structures, blood pressure regulation, we're going to talk about antidiuretic hormone. So we'll see this again throughout the semester. You'll generally see this released. Not only, I've been talking about if your blood pressure is a little bit low, so you can add that as well. But also when your blood solute concentrations are too high. If your blood solute concentration is a little bit elevated, antidiuretic hormone is released. If I retain water, my solutes are high, what happens to my solute concentration? It dilutes it out. I'm going to conclude our discussion here, and then I'm going to transition into our Unit 2 exam.